Okay, so this takes a little bit of time to get used to, but I want to be able to draw the picture for you. So if you can visualize it, I think it's easier to understand why it feels so, why things feel a little bit backwards. But first, I want to kind of talk about inverse functions. So inverse functions are functions where x's and y's are swapped. Okay. So for instance, if your x's and y's are swapped, your domains are also swapped. So for instance, these are inverse functions, okay, where any order pair that lives on one function, you're going to get a flipped version on the other. So if an order pair on a function has 1, 4, guess what order pair is going to live on the inverse function?
4, 1.
4, 1. Okay. Your x's and y's will be flip-flopped. Okay. So okay, so I'm going to have us draw this graph here. You put it in this space, this empty space here. Okay, so if you can imagine taking the two graphs and folding it over the line y equals x, they'll overlap. So if they overlap, you know that they are inverse functions. So it doesn't have to look like this, but this is just the one that I want to have us show you. Okay. So let's say we had a function f of x, and we had the inverse function f inverse of x. So that means every order pair that lives on this function, the flipped order pairs will live on the other function. So like you said, there's a 4, 1. Let's say there's a 1, 4 that lives on this function. On the inverse function, there must be an order pair that is 4, 1. Right? Yeah.
Why do you use prime to, oh, no, never mind.
Yeah, that's just the inverse. Yeah, that's the notation.
Sorry about that.
Now we know that this is the order pair relationship between a function and its inverse. So if you guys can draw another table here, I just want us to show that relationship between a function and its inverse. That means that if f of b equals a, then I know that the f inverse of a is equal to b, right? If there's an order pair AB on one, there must be an order pair B, comma A, right? Vice versa, right? So you know that a function inverse will always have order pairs that are flip-flopped. Now that's the function side of things. What does that have to do with us? We have to deal with derivatives. So the slopes at their corresponding points also have a special numeric relationship. Okay, so I want us to kind of visualize it here. So that means the slope here, right? This steepness at this point is going to have a numeric relationship with the steepness at this point. And I want to see if we can guess what that relationship is. Let's say the steepness here is 7. Okay, pretty steep slope. I'm just ballparking it. If there's a steepness of 7 here, guess what the steepness here will be? 1/7. That's exactly right. So that's it. That's really the entire relationship here. If I can figure out the steepness here, I don't have to do anything with this function. I know that if these are inverse functions at corresponding points, the steepness will just be the reciprocal, right? Not opposite reciprocal, right? These are both positive slopes, just one is steeper than the other. So if f prime of b is equal to 7, then the derivative of f inverse at a must be equal to 1/7. I know, sorry, I used 7 there, but maybe let me just change that to just n and 1/n, just so that I can make it more general. Notice that these are not the same points, right? These are different locations, but at their different locations, they are sharing a numeric relationship in terms of their steepness. Right. So what we're going to do with these problems is that we're going to be presented to find the derivative at this point, but all the information given to us is going to be at the other function. So we're going to do all the work on this side of things. We're going to find the derivative, and then from there, from here, we'll jump to our conclusion just based off of what we can gather here. Right. So I want to kind of give you a visual connection so that when we get to the messiness of it and it feels confusing, I'll just go back and point out where we are in terms of why we're doing certain things. Okay. So far, it makes sense. Okay. Okay, so let's look at example 6 here. We have a function x cubed plus 4x plus 2. And I want to find the derivative of f inverse at -3. Okay, I'm asking about the derivative inverse at a different point here. So I like to just go ahead and use this chart, and I'm going to make my way around it. This is what I'm looking for. This is my unknown. But by the time I work my way around this chart, I'm going to be able to gather everything that I need. Okay, so I know I'm looking for the slope of f inverse at -3. So if -3, we know -3 is the x value of the what? Of the inverse, right? So this at the first row, I'm going to list out all my order pair information. So f inverse at -3 is equal to, I don't know what the y value is, but I do know that -3 is the x value. But if -3 is the x value of my inverse, then -3 must be the what of my function, y value. So I know that f of some x value equals -3. I can fill out the chart up to this stage without looking at anything else, right? I know that this is the x value of my inverse, which must mean the y value of my f of x. Okay, so if I can fill this chart out, then the steepness here will lead me to the steepness that I'm looking for. So I'm going to use this to help me move forward. Where can I plug this -3 into this function? Right, that's my y value, right? So I'll set -3 equal to x cubed plus 4x plus 2. Right, let me bring everything over to one side, get 0 to show up. Now, this is not factorable, but we'll do guess and check. Okay, so we'll test different numbers until we find a number that works, but it'll be a number that's easy to find. Okay, if it's not 0, then it's going to be a number close to 0. If it's the test 1, then -1, then 2, then -2. At worst, it'll be 3 and -3. So you'll have just 7 numbers to test. Let's start with 0. Does 0 work? Does 0 make this equation true?
No.
No. What about 1?
No.
1 plus 4 is 5. 5 plus 5 is 10. 10
Give me something negative, I think.
Yeah, let's try negative. How about -1?
Yes.
Okay, so -1 minus 4 is -5. -5 plus 5 is 0. Okay, so we found the x value just by guess checking. So if I know x is -1. So -1 is the x value of my function. -1 is the y value of my inverse, right? So I've established my order pair relationship. Okay, there's an order pair of -1, -3 on one function, and on the inverse is going to be -3, -1. Okay, we know that they are different points.
So we will fill at the bottom left.
Yeah, so we're going to fill out the bottom left here. If I can find f prime of -1, then this slope will lead me to my answer. So how can I get towards finding f prime of -1? Yeah, take the derivative and then plug in -1. Yep. So if I find the slope on my f graph, then that's all I need, because this number will lead me to this number. I don't have to do any work on my inverse side. I can do everything on my function side. Okay, so let's find that prime of x. What's that prime of x? F prime of -1 is equal to 7. Okay, so I accidentally chose the same numbers here. But the slope of my f graph is 7, which means that the slope of my inverse at a different point, right? These are obviously different locations,
1/7.
is 1/7. So I like to use this chart and use this visual so that, because I think the biggest issue that students have is, wait, why are these different points, right? The reason why they're different points is because these are not on the same graph, right? These are across different graphs, but they have a unique relationship because these corresponding points have a slope that we can numerically connect with each other.
And that's like your final answers.
Yeah, that's it. Yeah, this is our final answer right here.
So you had to probably memorize that, like, the word each one.
Yeah, yeah. So the only thing you memorize is that your function and inverse will have flipped order pairs, and then at their corresponding points, their slopes will be reciprocals of each other, not opposite reciprocals, right? That's for perpendicular lines. You can visualize that these are obviously not going to be opposite reciprocals because they're both sharing the same. They're both positive slopes, right? They're both rising. Just one is a lot steeper than the other.
Will you ever try to like graph on these?
No graphing, but I do think the visual sometimes helps students see, right, why, why are there that relationship between those 2 points? Yes, question. You don't have to do this table thing. I just find it helpful. But basically, if you understand that a function and inverse will have order pairs, flip-flop, and their slopes will be reciprocals. But this is only something that's helpful. But if you don't use this chart, I'm not going to take off points, but this is how I'm going to present it. Okay, let's look at example 7. We have square root of x cubed minus 7. I want to find the derivative of f inverse at 1. So again, the chart just makes it easy for me to kind of keep track of my information. So 1 is the x value of my inverse. So I'm going to put all my order pair information up here. So 1 is the x value of my inverse, then 1 must be the what? Y value of my function. Right, does that make sense? I don't put the 1 in the parentheses. I put the 1 outside because they're not going to, one will be the x, the other one will be the y. So how can I use this to help me out, move to my next step? What's my next step? Yeah, set equal to 1, right? Make sure that you don't put this in for x because this 1 is not the x value of my function. This is the y value of my function. So we'll step to the side here. 1 is equal to the square root of x cubed minus 7. Now you can go through guess and check, but this is one where we can actually solve by hand. I can just square both sides and work towards solving for x, right? So if I square both sides, the square root will drop out. Add 7 to both sides. Take the cube root. What's the cube root of 8? 2. Okay, so I've established my relationship here. My order pair is 2, 1 on one and 1, 2 on the other. So if I can find f prime of 2, then whatever I get slope-wise will lead me to my answer. So if I want to find f prime of 2, I first have to find f prime of. Yep.
Fortune equation.
I got to find the derivative, right? So if I find the derivative, what rule is required here? Chain rule. So outside derivative times inside derivative. Sorry, running out of room. I'm going to take up some room from example 9 because example 9 won't need a lot of room. So let me just move this down here. Okay, let's plug in 2 to find the slope. So 3 times 4 is 12. 8 minus 7 is 1. 1 to the 1/2 is still 1. 1 times 2 is 2. So 12 over 2 is what? 6. So if the slope of my f graph is 6, the slope of my inverse at its corresponding point must be what? 6. So we're not doing anything on the inverse side of things. We're doing all of our work on the function side of things, and we're using that relationship to get to our answer. Okay. All right, 8 and 9 will feel even easier because all the work is already done for us. We just have to put everything, kind of line everything up, and then just make our decision. Yeah.
We always be like solving for the bottom right, like we're
Yeah, the way I have it, we're always solving for the bottom right. Whatever we're looking for, I start here and then I gather my information around the box.
Could there be a scenario where you go like you have to go backwards?
No, it'll be just this scenario. Yeah, you're always looking for the derivative f inverse at a point, but all your information is on the function side. So you got to kind of make your way to the function side and then make that conclusion and come back.
Also, what's the minimum information it can give you for you to be able to solve for it? Like,
oh, right. The minimum information is that I need the y value. Well, whatever is given to you is the y value of the function. So just always set that equal in for the y and solve for x. So either you can solve it by hand or you do guess and check. But if it's guess and check, it'll be an easy number, close to 0. Okay, example 8. It says that g of f of x equals x. So this just establishes that f and g are inverses. That's all it's saying. Whenever they give that g of f of x equals x, that just means if I plug a function into the other, they're going to cancel each other out. They're inverses of each other. Okay. So I'm trying to find f prime of 2. So I'm going to make my chart here. So I'm trying to find f prime of 2. I know that 2 is the x value of my f function, which must mean that 2 is the what? Y value of my g function. So I can always get to this stage without even looking at my problem, because I know that it has to be this relationship. So now let's just fill in the blanks, right? What from our given can we fill in and make this make sense? G of what is equal to 2? G of 7. So if there's an order pair of 7, 2 that lives on the on the g function, there must be an order pair of what that lives on the f function? 2, 7, right? 7, 2, 2, 7. We technically don't need this number, but I like to have students fill this in just so they can kind of see that, okay, I do see that flip-flop relationship here between f and g. So if I can get to g prime of 7, then that will lead me to f prime of 2, right? Do I know g prime of 7? 10. So if g prime of 7 is 10, then f prime of 2 must be 1/10. That's it. I think the biggest issue that students have with this concept is that when they see f of 2, they want to put the 2 in for the x value of the g, and that's where things get thrown off. Right? When they feel like the x value here has to go for the x value here, but we understand that you're going to get that flip-flop order pair relationship, then this is then you've gotten past the hardest part of the problem. Okay, you guys want to try example 9? Same process. Thanks. We want to find f prime of 3. So even without looking at anything else, I know I can fill up to this point. 3 is the x value of my f. 3 must be the y value of my g. Okay. What can we put in here that is given to us? G of 9. So if there's an order pair 9, 3 that lives on G, there must be an order pair 3, 9 that lives on F, because this tells us that we're dealing with inverse functions. So if I can find G prime of 9, then that will lead me to F prime of 3. Okay, what's G prime of 9? 4. F prime of 3 must be. Yeah. That's it. Okay, we're not going to have a quiz over this unit, but this is the quiz review that I've had in the past, which has kind of worked through it. So if you guys can go to page 9.
It's pretty sure you didn't say it.
Yeah, that's right. We'll be done with the unit by the end of this week. And we'll be able to start doing our test review. Our test will be next Friday.
This is you go over everything we learned on Friday.
Yeah, that's right. We will. So we'll start with number 6. Find the derivative of the function. This is on page 9. So the rule that we want to be able to eventually use is that we know the new rule for natural log that we learned is u prime over u. But we also talked about how whenever we have a natural log problem and we want to find the derivative, we always want to look for expansion properties, right? Because that will make life easier rather than dealing with a messy u value. So we have a couple of properties available to us. They're at the top of the page. If I have natural log of a times b, I can expand that into natural log of a plus natural log of b. If I have natural log of a over b, I can expand that into natural log of a minus natural log of b. And then if I have natural log of a to the nth power, I can bring that exponent down and make it n times natural log of a.
What do the U stand for, please?
Oh, the u just represents whatever is inside the expression. It could be x. It could just be anything in a set of parentheses. So here, this is a messy u value, right? But we can expand this if I use product property. So if I treat the x like the a, if I treat the square root as the b, I can rewrite this function as what? Natural log of x, what? Plus, good, plus natural log of square root. Now I can rewrite that square root as what? 6 minus x cubed to the 1/2. So the nice thing about log properties is that we can take a messy problem and split them up into easier workable problems. We can do one more thing here. This is already much easier than what we were doing here. We got to go through a product rule if we want to start our derivative process. But there's one more thing that we can do to make this even easier. What can we move here? That 1/2 can come down. That way we can avoid quotient rule for that second portion. So now our derivative should feel fairly easy because our u value are not going to be difficult for us to find the derivative. Okay. So these are completely separate problems. We can treat them like individual independent problems because there's nothing attached except for a plus or minus sign between them. And there's no parentheses connecting them together. They're not divided by one another. Okay, so y prime equals. So let's apply u prime over u. In this case, my u value is x. So what's x's derivative? Yeah, 1 over x. That's my derivative for my first expression. Plus 1/2 is staying. That's a coefficient. So that's not going to get impacted by the derivative. My u value is the parentheses. So what's the derivative of 6 minus x cubed? divided by 6 minus x cubed. That's it. That's our derivative. We'll do a little bit of cleanup, but I'm not going to ask you to find common denominator. You can just leave your answer relatively cleaned up within each fraction. Okay, everybody okay? All right, let's go to the back here. Number 10, find the derivative of the function below. This is a messy natural log problem. Let's take advantage of the properties so that we can split this up into maybe 2 easier problems. Let me clean this up one step at a time. First, I can rewrite this square root as what? I'm going to merge that exponent and the root together, so I can make it what? 5 over 2, yeah. Where can I put that 5/2 to make it easier to work with? Down in front, right? So no calculus yet. We're doing all the cleanup so that the calculus will feel easy. Okay, I got that exponent to come down as a coefficient. What else can I do before I jump into my u prime over u derivative? Quotient property, right? Natural log of a over b can be expanded into the natural log of a minus natural log of b. And the 5/2 will just attach itself to both my terms there. Right, much easier to work with because my u value doesn't have messiness with exponents. It's just a simple power rule to get to my u prime. Okay, so now we're ready for our derivative. Y prime equals 5/2 is a coefficient. That's not going to go anywhere. That's just going to hang out in front. Okay, u prime over u. -2 over.
Be 3x squared over x.
Okay, do some cleanup here. There's no need to find common denominators. No, no. We can just cancel out between numerator and denominator within this fraction. Okay, number 8. There's not much we can expand, and also there's something that we can't avoid here. We got to go through what if I want to find the derivative? Product rule. X cubed and natural log of x squared. It's not everything inside one natural log where I can expand. These are completely separate terms outside of each other, and they're being multiplied, so I got to go through product rule. Right. So f prime g plus f g prime.
Why is the log sign with the g?
I'm sorry?
Why is the log sign within the G? The natural log?
Because natural log is not a standalone. It's always natural log of something else. So there's always something inside the natural log. It's like tangent, right? Tangent of x, they're not separate. So natural log of x squared is one function, x cubed is another function. We could expand that 2 out, but I'm going to leave it alone because x squared is not difficult for a derivative. So, but yeah, we could bring that 2 down in front.
Yeah, but like when we're doing the product rule, do we keep the natural log in there?
Yes. Yeah. So let me show you what that looks like. We got f prime g plus f g prime. Now, when we get to the derivative, the natural log drops out because the derivative is u prime over u. Yeah. We could, I think, okay, I think what you're thinking about is this. If I have natural log of 3x squared, this I can't bring down because that 2 doesn't see the 3. But this one is fine because the x cubed is completely outside of that. I can bring that 2 down and be okay. Because, but this I can't, because if I bring that 2 down in front, these are not the same. If I do want to bring that x squared down though, I'll have to split up like this first, get that to be a standalone term, and then I can bring that down. Okay, what's g prime? What's u prime over u for this natural log of x squared? 2x over x squared. Do a little bit of cleanup here.
And the natural log sign goes away.
No, if it's part of my g function, it needs to stay. I can't just let it drop out. But okay, but it does drop out of my derivative, yeah.
Okay.
One of the x's cancel out. So I get 2x squared. This is 2x to the 4th over x squared, so 2x squared.
That's your final answer.
Okay, this idea of log differentiation is where you take the natural log of both sides. We introduce natural logs into the problem in the hopes of using the properties to expand out an otherwise messy derivative rule. Okay, so log differentiation means bring natural log into a problem that has no logs in it so that we can take advantage of those nice properties. All right. Okay, we prefer not to find the derivative at this stage, but now that we're inside natural log, I can break everything up. Basically, anything in the numerator can be split up using plus sign. Anything in the denominator can be separated using a minus sign. So your derivative will eventually look pretty messy, but your calculus process won't feel too difficult because you're just doing a bunch of individual problems. So I can put a plus sign between the two terms there. This is x cubed times the square root. I can rewrite that square root as 5 minus 4x to the 5th to the raised to the what? Well, that 5 is not outside a set of parentheses, so it's just going to be that 1/2 because that 5 only sees the x, doesn't see the entire expression. Minus okay, keep expanding, right? Because we can keep going using those nice expansion properties so that we don't have to deal with a messy U value, right? We can. Okay, let's find a derivative here. There's a little bit of implicit going on here because the derivative of natural log is u prime over u, so 1 over y times dy dx. I'm sorry, what did I do here? I brought the 3 down, but there's no, that 2 shouldn't be there. Okay, so now u prime over u for each of these terms, the coefficient will stay. I'm trying to solve for dy dx, so what else can I move over to the right side? The y, right? So the dividing by a fraction is the same thing as multiplying by the reciprocal. So the y comes over to the right, but I want to represent my derivative in terms of just x here. So I can replace the y back with what? With the original function. So it's going to look messy, but the process is not difficult because we're just, we're basically at the answer stage. We just have to kind of put it all next to each other. Okay, so there's my messy y expression. And then every term I just try to clean up within each fraction. I'm trying to solve for dy dx. So I have to move the y over to the right side of the equation. Well, dividing by 1 over y is same thing as multiplying by y, right? So this was y, but then I replaced the y with the original equation. Okay, let's do one more derivative of inverse at a point. So can we go to number 12 and try that one? Page 10, number 12.
What's number 12?
Yeah, number 12. Yeah.
Oh, that's fine. Unless you just like keep leaving them like that.
Yeah, I know it's messy, right? But you can leave your answer like that. Yeah.
There's no way you can simplify it.
Yeah, and yeah, with log differentiation, there is a way to simplify it, but there's no need. On the AP exam, they don't require it either. So, okay, so number 12, we want to find the derivative of f inverse at a. The a is 11, so here's our goal. Our goal is to figure out what is the derivative of f inverse at 11. But everything that we're going to be working with is on the function side. Okay, so you know that 11 is the x value of your inverse function, which must mean that 11 is the what of the function, the y value. Yeah. So this is how I can start off before I start working with my problem. The biggest mistake that students make is they want to insert that 11 in for the x, but whatever they give you is always the y value of the function. So our next stage is setting these equal to each other. Right? 11 is the y.
Well, then just choice.
So 11 equals 2x cubed. Set equal to 0. Okay, again, this is not something that we can factor, but we should it shouldn't be too hard to find that number, right? Let's test some numbers here. So can 0 make this a true statement? No. What about 1? Probably not. Okay. What about 2? Okay. 2 times 2 cubed, 2 times 8 is 16. 16 minus 6 is 10. 10 minus 10 is 0. So 2 works. So we know 2 works. Go ahead and fill out those order pairs. You know that there's an order pair 2, 11 that lives on the function. There's an order pair 11, 2 that lives on the inverse. Right? And we know that must be true because they're inverse functions of each other. So now it gets a little bit easier. If I can find f prime of 2, that slope is going to be numerically related to the slope of f inverse at 11. Notice these are not the same locations because they're across different functions, but their slopes will have, their steepness will have a numeric relationship. So how can I get to f prime of 2? First, find what? F prime of x, easy power rule. That 6x squared minus 3. What's f prime of 2? Okay. So if the slope has a steepness of 21 on the f graph, there must be a slope of what on the inverse graph? Well, number 21. That's it. Okay, so your homework is on page 12. Uh, 10 through 15. Oh. Okay, I'll send out a reminder and I'll send out the key so you guys can check your answer. So on page 12, 10 through 15 all.
What was the homework we did?
Page 5, all of page 5.
Questions? Let's talk went over on Friday evenings over today.
Pretty much we went over everything, yeah.
Okay.
You probably were you and expansion properties.
All right,
Yeah.
he's got to like learn which properties to use.
Yeah. Good, all right, thank you.
So your fantasy team won?
One of them won,
Oh.
but the other ones.
James Cook did pretty good. James Cook did pretty good. I think it's gonna be a stud for us for a long time. Pretty good. It's gonna be a stud for us. And, yeah. What's your record now? Oh, Bill, we're 5-3.
That's good.
Of course, right?
We lost the patient, so that's kind of.
That's the one win you wanted, right?
Yeah. We also lost it against too. And the Jaguars too. And that was like, they were a good decent.
Yeah. Daggers are getting better.
What?
So we're still trailing the Dolphins, even though we beat them. Still trailing by a game.
Yes.